Okay, good afternoon. Welcome back to Operating Systems. So if you missed the initial announcement, where's the chocolate? There's chocolate somewhere. There's chocolate up here, so go get that. I do not want any of it to be there at the end of the lecture because I will make poor dietary decisions like I always do, so please eat it. Okay, so today we're doing stuff that's more or less fun, still on topic, but not really covered in the exam, other than we're going to, revisit the concepts we introduced in the course. So your first question might be, what in the heck is a kernel module? So we know that there's user mode, kernel mode, and the kernel runs in kernel mode, has all the privileged instructions, all of that fun stuff, but we don't actually know how to program in it. Well, the Linux kernel is written in C, and you can write your own Linux code if you want, and that's exactly what we'll be doing today. Whoops. All right, so again, this will be recorded, so we will make a kernel module today, and that will just run in kernel mode. So it will be a bit different than regular C programming, other than we're still using the C language, but because we are in kernel mode, there's no standard C library, there's no printf, there's no malloc, there's no whatever, because it has to be contained all in the kernel, right? Whenever you boot up your machine, there is nothing. The kernel loads, and then the kernel is the only thing actually running. So we saw a little bit that proc file system, and we know that that's not actually real files because the file descriptors are wrong. But they kind of look like files. We can cat them, we can read them. So today we will actually create one of them. And when we create them, this kernel module, all it will do is count the number of running processes in the kernel. So if you read that file, it should just give you a number back. So it's pretty much all written for you. So we'll just go over it and explain it. So again, we don't have C, we don't have any standard headers, nothing like that. So all of the header files, because it's still C, they all begin with Linux because they like doing things actually well and have a proper namespace. So there's a few files we need. So we need a module. So a module is just a loadable piece of code that you can insert into the kernel when it's running. So the kernel, you can think of it as like a long running process. So whenever it starts running, and the only difference between that and your processes is it's a bit special in that it runs kernel mode code. So in order to insert code into it, it's not like we can just start up another kernel or like another kernel process or something like that. We have to actually insert code into the kernel and say, hey, Mr. Kernel, or Mrs. Kernel, whatever, hey, you kernel, please, here's some code, please execute that for me. And this is a way, there's some triggers that will like trigger loading for you. So you can say, only load this if you like find specific hardware, like if you're writing drivers or something like that. But we will just write a module that just loads whenever we tell it to. Then next header file we need, well, it doesn't have printf or anything like that, but they have a kernel equivalent of printf called printk, very clever naming, so print for the kernel. And then we want to create a file in the proc file system, so they have a header file for that too and a bunch of helper functions, so it's just called procfs. Then there's this seq file, so it's just a sequential file, so it's just like a normal kind of file that you just read and write bytes to, and that's because we're going to represent, that proc file system. It's just going to look like a regular file. And then since we're going to be looking at processes, well, there's a header file for sched, short for scheduling, that will contain all the information about processes, threads, everything like that. So in lab 3 now, when you had your thread control block, well, the things that are in that schedule is the process control block. So that will have all the information about a process, like it's stuff you had, like you had its thread ID, so in here it would have its process ID, and then it would have like a bunch of scheduling information and a whole bunch of other stuff. So how does a kernel module work? Well, like I said, there's no main, there's no nothing, so you have to kind of tell it what to run whenever it's inserted into the kernel and what to run whenever it is unloaded from the kernel. So there are two macros here called module init and module exit, and you're allowed to give it a function that runs whenever you insert it into the kernel and whenever it's removed from the kernel. So in the insert, that's when we're going to create our file. So we just have a PR info. So PR info, unlike when you have printf and it just outputs to the terminal whatever you write, there's different levels of debugging information. So there's different printfs. So you can say like, oh, this is a print log an error, log a warning, log info, log debug, and then you can selectively change whatever error or whatever level you want to see. So we'll just use the info level, which means just add some information. It's not super critical. So we'll print whenever we insert our module. Then here, there's a function called proc create single, which will just create a single file for us in that proc file system, and we will call it count. We give it some file permissions, then we give it this is some additional information that we don't have to give it whenever it's read from, and then you give it another function that says what should happen whenever someone tries to read from that fake file. So we'll give it a count show, make sure that there's not any errors, and it has a little bit different way of handling errors, but we don't really care about that for now. And the count show, all it's going to do is there's some magic we have to do. So this struct, task struct, that's what they call the process control block in the kernel. So this is the real thing. So if you're interested, you can actually go see all the fields. It's absolutely massive because it keeps track of literally everything about a process. And then all we're going to do is for each process. So there's a nice little macro that will actually traverse every single process on our system. And we're not going to use that task struct. We're just going to count how many there are. So we'll just introduce a variable called count, increment it, and then we will output to the file. So you can use printf, and then that will actually fake being that file. So whenever it's read from, we'll just print that count with a new line, and that's it. And then whenever we exit, all it's going to do is say, hey, it's going to print an error or print an info message, and then it's going to remove that entry from the proc file system. So it's actually not just floating there, not actually backed by anything. So we're running. We would compile it. So it's already built for us. And it's just an ELF file like we know of, but they just give it a little special extension. So it's called a KO file or kernel object file. But realistically, it's just an object file that's supposed to be a bit special. So if we want to insert our module into the kernel, there's this instmod command. So instmod will say, hey, go insert this code into the kernel. Then the kernel would run that initialize function in there. And then hopefully that creates that proc count file, and we can actually do some stuff. So before we do that, let's verify that in proc, there's currently nothing called count. So if we go through here, there's console, CPU info, crypto, config, command line, so there's nothing called count. And we'll go ahead, we will insert it into the kernel, and then all of a sudden, in proc, well, hopefully if everything has gone right, there's now a file called count. Cool. So, and it behaves like a normal file, so if we cat it, this will give us however many processes are currently running on our machine, and the code that counts that is running in kernel mode because we asked it. But under the hood, like this would just do a normal read system call, and then the kernel would be like, oh, when this person's trying to read from this file descriptor for proc count, it should actually go to that show function that we wrote, and then that's the bytes that should be returned. So you can see that's not a real file, we're just kind of faking it. So any questions about that? Kind of cool. So if we look at dmessage, so dmessage is a way to read all the messages your kernel is trying to print. So everyone that has called print k, it will print to this. This is a way to read the kernel's log in user space. So -L just shows everything that's at the info level. So here's when I was testing it earlier, and then here is when we just inserted the module. So we can see, hey, it actually prints off our message that we put in. So it says, hey, init, and we can actually see that there's a bunch of other messages that someone else printed to the kernel. So systemd printed some messages, and then the kernel is talking about, oh, it found some USB devices, So this is a fun way to figure out what your kernel's actually doing, and if you're just kind of sadistic and want to read some debug messages. But yeah, that's actually just code running in kernel mode. And if I knew how to do it, like we're essentially all safety is off. So this is running in kernel mode. So if I actually knew what instructions to call, I could crash my system. I could write random stuff to hardware. I could kill init finally if I really wanted to, because the kernel's not there to protect itself from itself. It assumes that you know what the hell you're doing. In this case, I don't know the exact way to kill the process, but we could do all sorts of like just really weird stuff, and there's no protections at this point. All right, any questions about that? So it's a real kernel module running in kernel mode. Yeah?
Why is a bunch of stuff red underlined? Is that just because kernel code is different from regular C code?
Yeah, so there's a bunch of stuff red underlined because like your IDE, like VS Code assumes C and like would read those header files. So I haven't set it up so that it knows where those header files are. So it doesn't actually know where those header files are, and all the other stuff depends on that. So it's just a bunch of red, even though it actually works. But yeah, I could get rid of the red if I actually configured it to actually look at the right header files. But yeah, so there's nothing stopping it. All right, any other questions? Because that was pretty much the whole plan today. Yeah.
So every time you like read that entry or read like the count directory,
Yep.
it is running this thing?
Yeah, every time I do a read, it will know to route any read to that file to this count show, and it would run this, and then this is what gets read. So I just always output a number, so it would change every single time I read the file. So let's see, proc count. So before it was 175, now it's 173. Some processes died in the meantime. So you can see every time you read it, it will be the number of processes that ran whenever you read from it. All right, yeah.
Are we allowed to ask questions for the final?
Yep.
Okay. Is the final cumulative, or is it mostly focused on the second half after the midterm?
Final is cumulative, mostly a focus. So where is it? So can I show you this? Probably. Let's see. So yeah, I can post the first page of it in the Discord. I was planning on doing that anyways. Well, first off, any like Lab 6 things I need to address? All right, then we can talk about the file. All right, so I'll probably paste they haven't confirmed it yet, but right now, if you want to write this down, I'll probably paste it in the Discord later. Questions, short answer, 20 points. Page replacement, 20 points. Virtual memory, 10 points. Processes, 10 points. Processes and threads, 10 points. Locking, 10 points. Semaphores, 15 points. Threads, 15 points. And file systems, 20 points. So total 130, goal is 1 point a minute. Yep, no?
You'll post it, right?
Yeah, I'll post the front page, but basically it's cumulative, but more focused towards the end, but it's like some stuff, if I give you any program and say, hey, I execute it, it's a process, so I can't really get away from that at all. So the review things are like, there's a straight up processes question, I think. I wrote it a while ago, so I kind of forget now. I have like a really bad short-term memory, so it's kind of good that I don't spoil the exam, but I think there's a virtual memory question, there's a processes question, and then that's about it. And then processes and threads combines the two. So if I have both of them, what happens? So the rest of the plan too is, so next lecture, do a little bit introduction in Rust. It will probably only be a very short time, and it will be related to threads and stuff. And then we can start doing like final review. I was going to bring up the past final I did, start it then, collect some stuff, and the very last lecture would also just be review. But yeah, all right. Anything else? Questions, concerns? Yep.
I think for the kernel module, I'm trying to run it on WSL using the Docker, and for some reason, you can't load kernel modules.
Yeah, so on WSL, you are not allowed to use kernel modules because it's Microsoft's version of the Linux kernel. So it's not like it's kind of a real kernel module, but not real. It's like a really weird thing. So yeah, you can only insert kernel modules if you actually have like a full-blown virtual machine that's like a real, what we talked about last time, like an actual type 2 hypervisor, or well, you don't actually need a type 2 hypervisor, but a real virtual machine, and not Microsoft's weird kernel. Because yeah, it is a Linux kernel, but it doesn't have all the same stuff. You're not allowed to load kernel modules into it. I actually don't know why, because you should be able to. All right, anything else? So final review, it shouldn't be that bad. It is cumulative, but it's not too bad. The short answer questions also relate to the beginning of the course, at least some of them. But there's not, yeah, it's more focused towards the end of the course that you actually haven't been tested on yet, because that makes sense. Yep.
Will the types of questions be similar to like a midterm where we have to like look at code and tell you what's wrong with it?
Yep. Yeah. Yeah. Code, like a lot of this is, I don't want you to write code from scratch because that kind of sucks on finals. There is one where you have to, I give you code and then say, fix it, please, or what has happened, or what should I do, things of that nature. So there's a bunch of examples where it's just a big code block and it's like, help. So yeah, it's kind of the same format. If you look at the website and do the CS 111 fall final, it's fairly similar to that one. Although this one's probably a bit tougher. Yeah. So yeah, like I said, that final's a good indication, and then just I tried to relate it to like questions that came up during the course and like what we could do to fix it. And if you know, so from the outline, obviously you should know how to center for. So I'll probably give you something like, you could probably imagine, here's some code, I want it to run in a specific order. How would you do that? Threads, you can probably imagine there's probably going to be a data race thing. It's like, oh, does this have a data race? Why? Yeah, things like that. But yeah, in terms of studying, as long as you did the labs, understood the labs, so like, you know, the virtual memory lab was meant to make sure you understand virtual memory, so that question will be related to that. If you did the lab, it shouldn't be too bad. Yeah, hopefully it's not too bad. Yep.
What kind of question is the virtual memory question? Because there's one in the past that was like virtual machines, but like it's not the same thing.
Yeah, virtual memory would be like, hey, here's a virtual address, and possibly here's some memory values. What would it be? Like if I actually use this and try and translate it. Which if you did lab 5, right, you know the steps. You start with the L1 or L2, hop, do. And yeah, here. All right, well, to fill time, we can start going over one quickly if we don't have any other questions. So, where am I at? So here is where it would be under courses. We got CS 111 full, final. So we can start going over them. So can we see that? Not really. So like the first question, page replacement. It's pretty much exactly what we had, right? Here's the following accesses. You have 3 physical pages in memory. Assume they're all on disk. Use the clock algorithm for this. Hint, probably a good one to make sure you know how to do. Oh, now use the optimal algorithm. Okay, well, great. Fairly straightforward. That should be more or less free marks. And threading, so we should know how to do this one too. So this one's a bit weird because we're calling fork within a thread. So let's look at the question. So we have int main, we have our socket, some comment that says, oh, we set up a socket, calls socket bind, all that fun stuff. While true, except, so this is obviously a server, although we don't really have to read this part to understand it, but it would create a connection. That file descriptor represents the connection. Then we create a new thread, and we pass the file descriptor to the thread, and we detach it. So everyone remember joinable and detached threads? Probably a good thing to know. And then within the thread, it gets the file descriptor, goes to sleep for 5 seconds, calls fork within a thread, and then checks if its process ID is 0 from the fork. That means this process is the child. So the child would dupe to FD1. So it would dupe that socket connection to 1, which is standard out, and then it execs ls. So it would basically just print the contents of ls to the socket. So this is like a remote ls, which is a fairly dumb thing to do, but kind of fun. So the questions would be something like this. Assume 4 clients connect. Each one makes it to the call to sleep 5, and okay, you need to scroll over. Stop it. All right, and none of them have returned for slept yet. How many threads are there in total, and where are they executing in the code? So in this example, yeah.
Professor, what is a client? I think it said. The 4 clients.
Yeah, 4 clients.
What's a client?
So a client just means someone, so this would be a server. So a client is just someone connecting to it. So 4 things would be accepted. So yeah.
Why is there only one parent process or main thread?
So whatever we start executing a process, like whatever starts executing main, that is a process, and it has one thread called the main thread that starts executing in there, if we want to think of it that way. So our process, by default, whenever you create a fresh process, it has one thread. So we have a main process, which has the main thread, and it would start executing this. And we said, assume that there are 4 calls to accept that succeed. So it would call accept, return a new file descriptor, create a thread, go accept 2, create another thread, true, accept, create another thread, true, accept, create another thread, and then it would be, after 4, it would just be, the main thread would be stuck, it would be blocked in this accept call, waiting for a new connection to come in, and we created 4 threads, right? So our main thread is sleeping, it's blocked in accept, and then we have 4 new threads that we created, and from the question, they'd all be stuck in this sleep. So in total, we'd have 5 threads. So first thread we start off with, and then we created 4 more. Okay, any questions about that? Okay, let's see if we can do the next one without. All right. all threads return from sleep and complete. What gets sent back over the socket and why? Which I kind of accidentally spoiled. So what does each person that connected see over the socket and why? Yep.
They would see the contents of the directory, like what's returned from ls.
Yeah. So each one would see the contents of ls in whatever current directory this is, which is probably more information than you actually need to answer this question. Just the contents of ls, whatever it prints. So, and that's because of this dupe, right? So we're replacing the standard out with that socket connection. So whenever we call execlp, it starts running ls. ls would just write to file descriptor 1, and file descriptor 1 points to the same thing as the socket. So it would just send all the output from ls would be sent over the socket. And this is essentially like a version of everyone's used SSH, right? It's essentially a really scuffed SSH that always just executes ls and doesn't care what you type to it. So if you wanted to expand upon this, hey, guess what? SSH kind of looks like this, minus, some security and all that stuff, but who cares about security, right? All right. So, come on. Okay, that's probably ruined. So how many processes did we create? And it says excluding the original process. Well, in this case, we would have created 4. And this question is mostly a hit that you also have. So I worded it this way, like exclude the original process. So you could be like, oh, wait, did that have a thread? Or why do you say exclude it? Should I have included in the first part? So that was hopefully to be a little hint. But in this one, we created 4 processes, excluding the main one because each thread called fork and created a new process. So then, oh no, what did we forget to do with the newly created processes? Yeah. Yeah, you have to call wait on them. We're awful parents, right? You always need to wait or at least argue about waiting. So it says, why is this especially an issue in a case where a server runs for a very long time and made up serving thousands of requests? So let's go look at this. So every time someone connects, we call fork, and we didn't wait on it, right? So we made a new process. It probably terminated because it sent something back, and then it is now in which state is the process in, that ls process in? Anyone like, what's the best zombie thing now, Last of Us? Yeah, so they're all zombies. So every time a client connects to it, we make a new process. It's called ls, like we make a new process, exec ls, and then we don't wait on it. So we create a zombie process. So every time someone connects to this, it creates a new zombie process, which just, why is a zombie process bad? Yep.
Because it uses up resources and it's process control block.
Yeah, so it still has a process control block. It's wasting resources. The kernel's not allowed to delete it because someone needs to read its exit code. All right. So yeah, so any questions about that? So you can imagine that if this runs for a really, really long time and like thousands and thousands and thousands of people connect to it, well, it's a zombie each time. Even if it's just every zombie only wastes like, 100 bytes or something like that, which isn't much. After a few million times, that's a lot of space wasted for nothing. So next question was, what would happen if we did not fork and instead just always executed dup2 followed by execlp directly after each thread? So this question just says, hey, essentially if I delete this, what happens? Yeah.
Since you only have one process, execlp would kind of replace the whole thing with the LS in there.
Yeah. So essentially, whatever thread makes it to this execlp first, well, I only have one process that is supposed to be the server that's accepting the connections, but execlp replaces the current running process. So the first thread that makes it to execlp calls execlp, and now my server process is dead. So it would have sent ls over the socket to one client, and then that process no longer exists anymore. So it would have been dead, wiped off the face of the earth, nothing more. So only one client would see output. The rest of the people would be like, oh, server not found, server's dead, or cannot connect, or something like that. All right, any questions about that one? Cool, on a roll. All right. Oh, what would be the issue if we remove pthread detach? All right, that's a good one. Yep.
Isn't it similar to not waiting, the problems with not waiting on the child process?
Yep.
Because you won't be able to clean up resources if you don't have the ether join as well.
Yeah. So it's pretty much exactly the same thing, right? Except we have zombie threads. So yeah, here we don't actually use the return value at all, and we don't need to join, but if we remove the detach, it's a joinable thread, which means that thread control block won't get cleaned up until you join it. If we never join it, then guess what? It's essentially the same problem as before where we don't wait. There's going to be a zombie thread that's going to waste some resources, take up a thread ID at the very least. All right, any questions? So yeah, that's a threading question, so that's pretty good. I can tell you from when I wrote the exam that this is similar-ish to what you have. So this one might actually be harder than the one I gave you. All right, yeah.
Professor, for question 2, what's the point of having like a thread create a child process? Why can't you just do it with the created thread?
Do what with the created thread?
Wait, you can. Oh, never mind. Okay, because you can.
Sorry, do what with the created thread?
Execlp.
Oh, yeah.
Run ls with the thread.
Yeah, so the reason we have to make a new process every time is because, well, in this case where we don't fork, whatever thread makes it to execlp first transforms the process, and now that server's dead. Right? So whatever was currently executing main, it's now that process no longer exists if we hit execlp. So it's replaced.
Okay, thank you.
Crap, I should probably rewrite your exam. What? Yeah, I did. Actually, I should probably stop talking is what I should do. Okay, locks. So we should be able to at least do this question for today. So locking, typically one of the hardest things we have to do. So you're given a transfer function to safely transfer funds between accounts. When did we see that before? Well, we had a whole bank sim, so hopefully this will be familiar. You decide to refactor it such that there's a separate function for deducting or removing funds from an account. Assume that multiple threads can call transfer simultaneously using different accounts. Consider your initial implementation. So here we have an account that has a mutex, it has a name, and it has an account or an amount. And then in transfer, we actually do check if from is equal to 2. So if you're trying to transfer to and from the same account, it just returns and doesn't do anything. So you don't have to worry about that. Otherwise, we will grab the lock for the to account, then call deduct and actually add whatever we take away from the from account, and then unlock the mutex. And in the deduct account, well, we grab the lock for the account, which in that case is always from, and then we check if the amount, if it actually has enough money in the account. Otherwise, we just give 0, which means it won't do anything, and then we unlock and then return the amount. Now, first one says, does this code have any data races? Come up with an example of data race it does, or justify why it does not. So, give you a second, or give you a little bit to look at that and see who wants to justify some data races. Oh, also the teaching station is broken, so I can't read the Discord chat, and I can't read it from this angle. If someone wants to repeat it, if it's...
Is there someone asking if the exam will be more difficult because the midterm was had a high average?
Midterm wasn't like super high, was it?
83 is pretty high average.
Oh.
I mean, I wouldn't object to having an 83 class average, but
What are you talking about? 83 is such a low average,
yeah, you're
right?
right. Sorry, my bad.
So-
my bad.
So much higher. We expect so much higher.
So like,
Every other class is like a 95 average. Of course.
so it's like, what's the realistic average that it should probably be, as opposed to like what you guys are used to? So like a goal average is probably like, I don't know, like 75 or whatever ish. 80, like I kind of set it so that, you know, if it was an average class doing average, it would be 75. Hey, you guys are better. It's fairly objective, I think. I think looking at 80,
I agree with that.
yeah, I think 80 was fairly fair for that. I don't know. Like, it's like, well, what's the exam supposed to test? If everyone just fails it, and like the exam average is 50, and everything gets scaled up, and it's like, does that really evaluate how well you learned anything? Probably not. It's like evaluates how well you can suffer. So, yeah, I'm not terribly concerned. I'm more concerned about that midterm average with the labs pushing up. So, yeah, but we'll see if the university yells at me. So far, in my whole history of teaching courses, I've never curved a grade or adjusted anything. So, if the university yells at me, so be it. Because, yeah, I think the labs are probably weighted a bit much, but I guess we'll see. All right, anyways, this question, yeah, data races. Yep.
There's no data race because, like, any point where you're modifying any of the variables, they're already logged.
Yeah. So in this case, whenever I modify any of the variables that are associated with the account, I have the mutex for that account, so there's no data races because only a single thread can run at a time within that lock and unlock, also called a critical section. So I don't have any data races because a data race, remember the definition for data race, 2 concurrent accesses and at least 1 is a write. In this case, I only have 1 access at a time, so I don't have that problem. So like here, I add to the 2's amount only when I have the 2 lock. Okay. And then here, I only subtract from this account's amount, which I guess in this case is always from. So I only subtract from that account only in the case that I actually have this lock. Here, I just return the amount. I'm not actually modifying anything. I just return whatever I read. Yep.
So like for transfer function, like you didn't have a log for the from account. So what if when you are deducting and then the
So yeah, there's some points where like it might be a bit different depending on, you know, the order, but if you're at that granularity, the order, it's not really deterministic anyways, because if you like transferred, like did one transfer and then the other, that's different than doing the other transfer first and then the other. So that's not a data race. Data race is like bad values, but this is just the order of transfers we can't really determine. So in this, we don't have any wrong answers, but you know, if they're close enough, we don't have any guaranteed order between transfers because it's just the way it is. Okay, so yeah, does not have all accesses to the account's amount protected using their single mutex, includes reading and writing, and subtracting funds or adding funds to the account. So next question, does this code have any deadlocks? Uh-oh. Come up with an example of a deadlock if it does, or justify why it does not. All right, so we'll go back there. All right, so now deadlocks. Yep.
I don't think so because you're never grabbing two locks, or you're never trying to grab like another one after already grabbing the first one. So.
Is that true? Yeah.
I think if we transfer from A to B and B to A, then the first one would block A and the second one would block B, so you would have a deadlock, right?
Yeah, but back onto your first point where you said I don't, so one of the things you said is I don't have a lock, don't try and get a lock while I already have one. So, well, that's one of our conditions, so let's just read it. So imagine we have account from A and to B. Well, we would have to acquire lock A first, then we would call deduct, and then we would try and get this mutex. So we have lock A, and then we try and get lock B. So that's already not a comforting sign. Yep.
If you have two threads, for the first thread, the to and from are the from and to of the other thread.
Yeah.
Then maybe the first thread could acquire two, and then context switch, where the other thread will grab the other lock.
Yep.
And you're just waiting on each other.
Yep. Yeah. Yeah. So we've identified that at least initially that, hey, there's a case where even with a single thread, when you have a lock, you tried to acquire another lock. So that should be setting off like alarm bells. I don't know the reference for you guys. I would say like the red alert thing, but probably no one watches Star Trek probably. Yeah, I don't know what the reference is, but anyways, that's a bad sign. So if I have a transfer from A to B, and also I have a transfer from B to A, well, in another thread, well, what could happen is one thread goes here. So this, let's say it's A and then B. Well, it would try and acquire lock A, and then we could context switch over to another thread where its from is B. So it would try and acquire lock B, and it would get it. So now thread 1 has lock A, and thread 2 has lock B. And now whenever they call deduct, they would go into this lock, and then within the lock, well, guess what? They're trying to acquire a lock held by another thread, so they're deadlocked. So answer is yes, we have a deadlock. So, and here's where it is. So like I just said, if we have one thread A to B and another thread B to A, then we can have a deadlock. All right, so it says, given the issues you found, so we found that there were no data races, but we did have a deadlock, so that's not good. So explain how you would fix the code to prevent these issues, and it says you may not significantly refactor the code. That means that transfer must add to the account and call deduct, and deduct must safely decrement the account only if it won't have a negative amount. Otherwise, it must be 0. Deduct always returns the amount deducted. You may write replacement functions or explain yourself clearly. So what would we want to do? So it's kind of a roundabout way. Yeah.
So I think you would want to not lock the two accounts from the beginning. So you save the deduct, like the result from deduct to a local variable, and then you get the lock for two, write it, and then unlock. So you don't have two locks at the same time.
Yeah, so his suggestion is we just essentially save the amount from deduct, save it to an integer or something like that, and then only after that we get the mutex for, or acquire the mutex for 2, then add the amount and then deduct, or then add the amount and then unlock it. So that way we don't have 2 locks at the same time. So that seems credible. Any other ideas? Yeah.
You can always lock the account with the lower ID first, assuming they do have account IDs.
Yeah, so here they have names. So they don't really have account names. So let's see. So this essentially has the idea that he explained. So in this case, we just don't hold 2 locks at the same time. So we just call deduct. Deduct locks from and then unlocks from before it ends. So whenever we return from deduct, it's safe, has no data races, we don't have to change anything. We just save that amount, and then after that, we can grab the mutex to 2, and then add that amount, and then unlock it. So this is safe because we're only adding funds to another account, right? We only do one at a time. We don't have hold and wait or anything like that. So we came up with a third solution. So to prevent a deadlock, we can either always acquire the mutexes in the same order for every thread, or we could not do hold and wait. And in this case, we just eliminated hold and wait. And there's 2 ways to eliminate hold and wait. So just don't acquire another mutex while you have one. Or if you have a mutex, you have to be able to give it up with that try lock. Yep.
So does this mean that you can deduct from like say twice in a row before you add to anything else?
Yeah.
Is that not like a problem?
Yeah, so this doesn't have any data races and it won't deadlock, but you could argue that if you get really unlucky, it might break like what a transaction should be, which is like a problem specifically if you actually like ran a real bank. But in terms of deadlocking and data races, we don't have any of those. But yeah, it's a bit silly in that if you actually had a bank, you would actually care about a transaction as a whole thing. So you'd need a slightly different approach. But yeah, your example on the exam doesn't use a bank.
Is it a big deal if it deducts twice in a row? Because I mean, if the amount is 0, it just doesn't go below 0, right?
Yeah, it's not too big of a deal if it deducts in a row because it will never make it go negative. I believe if you think about it really, really hard, you can see some weird orderings where like, if you have a large string of accounts where you expect it to be transactions, then it might be slightly different answers than what you expect. All right, well, oh wow, another locking question, great. So this one I would probably title for your exam, Semaphores. So this one is probably, this one's way longer than yours, but yours might require some more thought. But I'll probably leave this one for next lecture. And yeah, hopefully we don't, so fill the Discord with questions and stuff for your exam. Like the last day, we're gonna have lots of time to do essentially whatever you want. So we've done like the first 3 questions of this exam, which is like, I think there's only 8 questions in total. So we've already done like almost over a third of the exam. So yeah, so that's pretty much it. So, oh, right. Fill out your course evals, please. No, I can't threaten you, never mind. Just please do it. Your midterm grade is great. That means you should be nice. Oh yeah, the design fair also starts tonight for ECE if you want to see some projects. I have one group tonight and then 2 tomorrow. So they start, it's My Hall 150 at 8 for the public, I believe. So if you're around, you can check that out if you want to see what fourth year projects look like, get some ideas for yours maybe. So yeah, that's pretty much it. So just remember, pulling for you. We're all in this together.